last two talks of today. Next speaker is Luis Garza from Universidad de Colima here in Mexico, and he's going to talk about higher order Sobolev-type inner product for polynomials in several variables. Luis?
Okay, well, I want to start by thanking the organizers. Thank you for the invitation. This is actually my first time here in Cuernavaca, and I'm very happy to be part of this workshop in honor of Professor Natig. I also want to thank, but it's not here, Ivan, because his talk is very related to this one, and he already mentioned some of the things that are necessary to understand orthogonal polynomials in several variables. So this is the contents of the presentation. Just very small introduction about orthogonal polynomials in one variable, because this is something that most of the speakers today have talked about. Again, another short introduction to orthogonal polynomials in several variables. Then the problem that we are solving here related to a certain modification of an inner product in such a way that you have a Sobolev-type inner product in several variables, and we're going to obtain some properties associated to the polynomials which are orthogonal to this inner product, and then some asymptotic results for one particular example of a measure which is supported in the unit on the unit ball in d dimensions. So this is very well known. You have this is one variable. You have one positive measure mu. You have an inner product in this way, and you can get a sequence of orthogonal polynomials, which is orthogonal with respect to this inner product if the degree of every polynomial is n, and the inner product is 0 for different degrees and different than 0 for the same degrees. So this is something that a lot of people have mentioned today. We will mostly use the monic normalization. These are the most known examples which have appeared in several talks. These are the classical orthogonal polynomials when you request that your orthogonality measure is positive. So you have the Jacobi, Laguerre, and Hermite polynomials. They have several properties, some of which have been mentioned here. Now the zeros are real, are simple, and are located always in the interior of the complex hull of the measure. The zeros interlace. I mean, the zeros of two consecutive polynomials are interlaced. And they are polynomial solutions for some second-order differential equations, which we have heard before here. Now, they also satisfy a three-term recurrence relation, which is this one. Something that I believe has not been mentioned today is the reproducing kernel. It is a polynomial that you can construct in this way. You need all of the polynomials of degree n and below, and you construct this polynomial which has this important property, which is a reproducing property. The integral of any polynomial of degree up to n with respect to this kernel is just the polynomial evaluated in the second variable of the kernel. So this is called reproducing kernel, and it is important here because I will be defining something which is very similar to this, but in several variables. Now, when we talk about orthogonal polynomials, some of the problems that are studied is modifications of perturbations of inner products. One particular kind of these perturbations are the so-called Sobolev-type inner products, when you add some masses here and some Dirac deltas with derivatives in order to create an inner product that is not standard. So in the case that j is equal to 0 and you don't have any derivative here, what you get is the Kral polynomials, which Antonio talked about yesterday. But in general, you can add a finite number of Dirac derivatives here and evaluate at some point, and some real masses that are taken positive if you want this to be positive. So normally you study the cases when this measure is a classical measure like Jacobi, Laguerre, or Hermite, And the type of problems that you study when you consider this modification of the inner product are related to algebraic properties, such as connection formulas that relates your original polynomials with your perturbed polynomials. Sometimes you also evaluate how are the zeros of the perturbed polynomials, and some other asymptotic properties like relative asymptotics. Sometimes you want to study how these polynomials associated with this inner product behave with respect to your original polynomials. Sometimes you also study how the zeros behave and so forth. So the plan here is to extend this kind of inner products to several variables. So in order to do that, I first need to mention a brief introduction on polynomials on several variables, which is something that Ivan talked about in the previous talk. First, I will be considering here not only two variables, but the variables. So we will need some multi-index, which I call alpha, and it has the components. We also define the length of the multi-index just as the sum of all of the components here. And in this way, if you have a point in the dimensions, then you can consider just this power, just each component of the multi-index is associated to one of the variables. So you have this power, and it means this expression here. So the length is called the total degree of the polynomials. So in the case of Ivan, he was here talking about total degree 2, so you have polynomials which have degree 2. Now, of course, in this case, you have to change a little bit the definition of orthogonality because of the following. We will say that you have a polynomial in the variables. It's just something that has this form. These C are real numbers. And this is notation. This gamma D is the set of polynomials of several variables with real coefficients. And when you put a subindex here, n is just the maximum total degree that you allow. So if we are given with a domain G and a positive measure on that domain, we can define this inner product for polynomials in several variables. And we will say that one polynomial in this linear space is orthogonal with respect to the inner product if the inner product is 0 with respect to any polynomial of lower total degree. So that's the definition of orthogonality here. Now, the problem here is that when you are considering polynomials with total degree n, which are orthogonal with respect to the inner product, so you have a lot of combinations in the polynomials and the exponentials of the variables, such that the total degree is n. So basically, how many combinations you have this number. In the case of two variables, this is 2. For degree 2, in two variables, this is 2, this is 2. So this you have the combination in 3 on 2, which is you get just 3 polynomials. But of course, when the degree is up and when you have the variables, then this number can be very large. So this number is given by this combinatorial number, and this is just notation. So when I talk about R and D is all the possible, a vector, I mean the dimension of the vector that contains all polynomials of total degree n in the variables. So that's just notation. So we can get a basis of this space, and this is the vector that I was talking about, and this vector is just this one when n is equal to 2 and the number of variables is equal to 2. But in general, if you have a bigger degree and a bigger number of variables, but this is a very large vector. So the dimension is just this number. So one fundamental difference between polynomials in one variable and polynomials in several variables is that in one variable, and this is something that Ivan mentioned, you have a natural order of the basis. So you can just order by degree. But in this case, you have a lot of different ways to arrange the basis, and every different basis gives a different sequence of polynomials. So that's why this problem of analyzing polynomials orthogonal in several variables is a much complicated one. So we choose to arrange these elements in some order, which is lexicographic order. And that's the order that we will use in all the presentations, but we can use very well any other order, and these results are basically the same. Now, this is what we call an orthogonal polynomial system. We don't talk about now orthogonal polynomial sequences, because this is a little bit different. So the orthogonality means the following. I will say that two vectors of different total degree are orthogonal if this inner product is 0. This means these are vectors. So when you multiply this, you get a matrix. So basically the notation is that you integrate over every element of the matrix. So that means that when you do this operation, what you get is a matrix. So if the total degree of these vectors is different, then you have the 0 matrix. And when they are the same degree, then you have a matrix, a square matrix of size R and D, which is symmetric and positive definite matrix. And so we have a definition of orthogonality which is a little bit different than the scalar case. Now in the case that these matrices H are the identity for every n, then we just say that the polynomial system is orthonormal. So this is very natural. So an example. This is something that I believe is similar to the examples that Ivan showed before. You can construct polynomials which are in several variables. Basically, you can take two measures, two wave functions in two different, or could be the same intervals. And you define, you pick a function which has some conditions. And then you consider the sequence of orthogonal polynomials in one variable which is associated to this measure. This measure here is an example of a transformation that Antonio mentioned yesterday. This is a case for a Christoffel transformation when you multiply a weight for some polynomial of some degree. So this is like polynomials associated to some Christoffel transformation of the weight omega 1. Now, if you denote the polynomials associated with this measure with this notation, and you call Q to the polynomials associated to the other weight, then you can construct these polynomials into variables which are orthogonal with respect to this inner product, where this weight in two variables is just this one. And the area of orthogonality is just this rectangle here. So this is more or less a systematic way to construct families of polynomials which are orthogonal in two variables. I'm not sure if this can be generalized to several variables. I'm not sure about that, but the examples that I've seen are with two variables using this method. Now, okay. So in general, and this is something that Ivan already talked about, we can consider vectors which contain only monic powers of x. So this is just this one. The one in the case n equal to 2 is just this one. Of course, when n is bigger and you have more variables, this the length of the vector is going up and up. So if you have a system of orthogonal polynomials in several variables, then you can decompose this in this way, which is very simple, which is actually the same like this one. So what I'm saying here is that this is a square matrix where it's always invertible, so you can multiply by the matrix, and from here you obtain just this one in the case n equal to 2. But this is more general to any degree, but it's just the same thing that Ivan wrote here. So there are more things related to polynomials in several variables. They also satisfy a recurrence relation, but now since these are vectors with different sizes, then you have some matrices here. And the difference here with respect to the three-term recurrence relation that satisfies the polynomials in one variable is that now you have as many recurrence relation as the number of variables that you have. So in the case that Ivan mentioned before, it's just two sets of matrix. Now we have just D because we have D matrices. So this is it's basically the analog of the three-term recurrence relation for polynomials in one variable, but now you have several recurrence relations. There are some conditions for the matrices. This is just the case, the symmetric case. When you consider orthonormal polynomials, then you have some symmetry in the matrices. This is just the monic case. You have some rank conditions in the matrix, the rank of the A and the C in the previous slide, these two. Has to be the same. It has to be this dimension here. So the rank of the matrices is very related to the dimension of the vector of the polynomials of some fixed total degree. Now, remember that I was talking about the reproducing kernel for orthogonal polynomials, that we define something which is similar, but now in several variables. We have these matrices that are the equivalent of the norm of the polynomials. This is matrices that appear in the inner product. Then we multiply this, and what you have here, when you multiply what the corresponding vector of polynomials, you have just one polynomial in several variables that you call just Pj, when j is the total degree of these two vectors. And we define the kernel function just adding up all of these functions for all the degrees up to n. So this is very similar expression to the one that I showed for the reproducing kernel, but this is not called a reproducing kernel because we don't know if there's a reproducing property for this. So we just call that the kernel function. Now the good thing about this function is that regardless that when you have a different order of the bases and you have a different polynomial systems, this function is always the same. I mean, it doesn't matter what basis and how you arrange the basis, you always get the same function, the same kernel function. So when you are going to analyze the, let's say, asymptotic behavior associated with some family of orthogonal polynomials, you usually don't analyze the polynomials themselves. You construct these functions and analyze the function because this function represents the measure and is invariant from the basis that you choose. So that's the reason that this function is important. So this is what I mentioned. The orthogonal polynomials are not unique, but this one is unique in the sense that it doesn't depend on the basis that you selected. Now, from now on, we will assume that the polynomials that I'm considering here are orthonormal. So these H's, these matrices here, are the identity. Now, my goal here is to generalize the Sobolev-type inner product that I mentioned at the beginning. And that includes some derivatives applied to some delta, Dirac delta. So when you have several variables, that you need to apply gradients here. So this plays the role of the derivative, of course. And of course, when you apply the gradient to a polynomial of several variables, then what you have is a vector whose entries are just the partial derivatives with respect to every variable, right? So this is just notation. This just means that you apply the gradients to this polynomial and then you evaluate at the point x equal to theta. Now, we can extend the gradient operator to a vector system of polynomials. So instead of having just one vector here, now what you have when you apply a gradient to a vector like this is you have just a matrix, right? A matrix of this length, and the number of columns is the number of variables that you have. So in this case, you have a matrix whose length, number of rows is just this combinatorial number, which depends on n and the number of variables, and the number of columns is the number of variables that you have, because every column contains the partial derivatives with respect to one of the variables. So you get you start to get some more complicated objects here. So when you want to apply a higher order gradient, then what you get is your matrix is growing and growing and growing. So you have just a matrix of this size, and here, since you are applying derivatives of higher orders, then you have all of the derivatives are crossed. I mean, you can have some derivative with respect several times with respect to one variable, and some other times with respect to another variable. So basically what I'm saying here is that these betas here are just all of the possible ways that you can apply j derivatives in several variables. I mean that the total order of derivative is just j. So you can apply, the first one could be when you apply j derivatives with respect to the first variable. And the last one could be when you apply j derivatives with respect to the last variable. And in between are all the possible combinations, right? So this is a matrix that contains derivatives. So based on that, we can define the j derivatives of the kernel function. So if I consider the kernel function and make the derivative of order j with respect to the variable x, this is the notation and this is what it means. So to the first vector you apply the j order gradient and the other one is left without derivatives. And if you want to apply the derivatives with respect to the second variable, then you put just the gradient in the second term. Of course, these are, what you get here are just vectors. Here are the dimension of the things that you are obtaining when you apply several derivatives. Now you have the symmetry here, which is important. And lastly, we can consider a matrix which contains all of the possible j derivatives with respect to two variables. So what you get here, the first element of this matrix could be this kernel function when you applied j derivatives with respect to x and no derivatives with respect to y. And then when you go to the row, you are changing the order of the derivatives. And the same for the column. So this is a matrix that contains derivatives of several orders with respect to x and with respect to y to the kernel function. So I think this is like complicated notation, but it has to be this way. So one particular property of this matrix is that it's positive definite. So when you multiply by some real number and you add the identity matrix, this matrix is also symmetric and positive definite. This is something that we will use later. So this matrix is very important because it allows you to express the polynomials orthogonal with the Sobolev-type inner product in terms of the polynomial associated to the original inner product. So what we're doing here in other words is just consider one family of polynomials with respect to one inner product. You modify the inner product, you get a second family of orthogonal polynomials, and you try to relate them. So that's the plan. So this is the inner product that we consider, which is the analog of the Sobolev-type for one variable that I mentioned before. So you define a Sobolev-type inner product, which is defined as the original inner product plus some discrete part that has to do with the gradients of some Dirac deltas evaluated at the point x equal to theta. So this is positive definite. So that means that we have a sequence of orthogonal polynomials or system of orthogonal polynomials that are orthogonal with respect to this one. And we will call those polynomials Q. So the normalization that we will use is that if the polynomials associated with this original inner product are orthonormal, then the normalization of these perturbed polynomials is such that when you make this difference here, what you get is a polynomial in several variables of degree n minus 1. So you just choose the coefficients of these polynomials so to be the same of the coefficients of these polynomials. So when you make the difference, all of the total degree, the higher total degree goes away, and you get just this is a vector of polynomials whose total degree is lower than n. So we choose that normalization. Now that means that we can express the new polynomials or the perturbed polynomials in terms of as a linear combination of the original polynomial. This is very well known. These are some sort of Fourier coefficients, and it's more or less easy to obtain. In an abstract sense, it's very well known how you can compute these coefficients, which depends on the inner product and depends on these quantities here. So it turns out that at the end, what you have is the following. If you consider the inner product that I just mentioned, if you call P the polynomials associated to the original inner product, and you denote by Q the polynomials associated with the Sobolev-type inner product, then those two families are related by this expression. Of course, when the total degree is smaller than J, then you have the same polynomials, but when the degree of the polynomial is bigger than the order of the derivative, then it's when you start to getting changes, and you can obtain this vector of polynomials, like this vector of polynomials minus this thing. And in this expression appears the matrix that contains the derivatives of the kernel function. So that's why this is important. This is always invertible because this matrix is always positive definite, so we don't have any problem here. Now, there's a converse result. If you define the polynomials in this way, then you can prove that there exists a functional or a measure or an inner product such that these polynomials are orthogonal with respect to that inner product. Now, we can also obtain expressions for the norms associated to the Sobolev-type orthogonal polynomials. The G's are the analogs of the H's, the matrix H that I mentioned before. When you get the inner product of the original inner product for the P's, for the original orthogonal polynomials, you have a matrix which is the norm, which is H. Now, if you want to calculate the norms associated to the Sobolev inner product, it's just this very ugly expression that, of course, contains information about the matrix of the kernels and the derivatives. So once you have these norms, you can define the kernel function for the Sobolev polynomials in a similar way. So you get these polynomials, you multiply by the inverse of these matrices, which are also invertible, and you define the kernel function here. Now you sum everything here, and you define the new kernel function. So this is, the same object, but now for the new inner product. So since we know that this kernel function is independent of the order of the basis that we choose, so it makes sense that if you want to study the behavior of these polynomials, you need to use this kernel function. So we have the following relation between the two kernels. This is the original kernel, this is the Sobolev kernel, and the difference between the two is just, again, an expression like this. So basically, if you were to estimate the difference between these two things when n goes to infinity, you need to obtain the behavior when this thing goes to infinity. So of course, if this goes to 0 when n goes to infinity, then these two kernels are equal asymptotically. So that's basically the plan. But unfortunately, we, in general, for polynomials in several variables, there are not many results related to the asymptotic behavior, not for the Sobolev-type orthogonal polynomials, but for many orthogonality ways. So basically, there are several examples that we know when you can say something about the behavior when n goes to infinity of a sequence of orthogonal polynomials. So that makes very difficult to obtain results of the behavior of this kernel function for one particular measure. I mean, you cannot take an arbitrary measure and obtain the behavior of these two guys because you don't even know how this behaves for the original measure. So if you want to obtain some explicit results for this, you have to take one known measure that you know the behavior of this one, and you can calculate the behavior of this one, so you can say something about the behavior of this one. So these kind of things you only know for a very small quantity of examples. And I will show one example here. This is more or less well known. This is called the classical weight for orthogonal polynomials on the unit ball. We're talking about a ball in d dimensions. This mu is just a parameter, and this c is just a normalization factor, so you have just orthonormal polynomials. And when you consider the system of orthogonal polynomials associated with this weight, then you can say something about the behavior. I think there are some other results in the simplex and not much more examples. So these are the very well-known examples. So this is the one that we took. And we basically consider a special case when j is 2, the number of derivatives is 2, when the point when you add the masses is 0, and in that case we can calculate asymptotic formulas for the kernel functions at the derivatives. So basically the behavior will depend on the number of dimensions and on the location of the point. In this case, for example, if you take the origin, then this thing behaves as n to the d plus 2. If you take points on the unit ball which are inside except for the 0, then the behavior is this one. And if you have points in the boundary of the unit balls, then the behavior is this one, which depends on mu, which is a parameter on the measure. So you basically have 3 different behaviors of the kernel function and the derivatives. One for the case that x is in the origin, in the inside of the ball, and in the boundary of the ball. So that means that if we want to calculate the asymptotics of the Sobolev-type kernel function, then you have 3 different asymptotics, one on the origin, one on the inside, and one on the boundary. So basically, when you calculate the measure, the matrix associated with the derivatives of the kernel, the matrix turns out to be very special. Is a block matrices, and this expression here, I didn't write the explicit expression for C1, C2, and C3. There are quantities that depends on the orthogonal polynomials associated with the weight function that I just mentioned before. So these are these things just depend on the original polynomials. So what is important here is that this matrix has a very well-defined block structure. So there's a big block here in this form, and there are a series of smaller blocks here, 2 by 2 blocks, this quantity of blocks. And this is always the same. This block gets repeated until the end of the matrix. So in order to obtain the asymptotic behavior of this matrix, we just need to know how the C's behave. So basically the C1 behave like this, the C2 behave like this, and the C3 behave like this. So this C1 and C3 have similar behavior, and C2, which is this one, behaves in a smaller speed. So the main result is this, associated with that example. If you were to analyze the behavior of the Sobolev kernel function and the original kernel function, then you find that this difference diverges when you are on the origin with this speed. When you are at points inside the unit ball but not the origin, then this goes to 0. So they are the same. And when you consider points on the boundary of the unit ball, then this difference goes to 0, but only when the parameter satisfies this condition. So you have 3 very different behaviors depending on the point when you want to know the asymptotics of this kernel. And that's basically it. These are some references, and these results are contained in this paper. I forgot to mention at the beginning that this is a joint work with Herbert Dueñas from Colombia and Miguel Piñar from Universidad de Granada in Spain. And most of the results that I showed when I was introducing the polynomials in several variables appear in this book of Dunkel and Chu. And there are some other similar problems that are studied in this paper by the people in Granada, Miguel Piñar and Teresa Perez and so on. So this is all. Thank you very much.
time for questions. Natig.
Luis, just out of curiosity, I want to ask you maybe stupid question. Can you give example of the one variable Sobolev-type orthogonal polynomials which still could be written analytically? Do you have example? For example, if I ask you to give an analytical expression for Hermite polynomials, you will write down sum, right, or some sum, or hypergeometric representation for the Hermites. And for Laguerre, you can do that, right? But for Sobolev-type orthogonal polynomials, even in one variable, is it possible to also have explicit expression?
Well, we have is connection formulas. So you can, I mean, it's something very similar to this one. In fact, it has basically the same form. So when you are considering polynomials in one variable, and you construct a Sobolev-type inner product, what you get is that the Sobolev-type polynomials can be expressed in terms of the original polynomials using an expression that is very similar to this one. So it's not I mean, if you have a closed expression for these polynomials, then you have a closed expression for these polynomials as well. But so yeah, you have connection formulas, but I'm not sure if the Sobolev polynomials can be expressed in terms of a hypergeometric function. That I don't know. But we do have connection formulas. So if you know your original polynomials, then you can construct the new ones. I mean the Sobolev ones.
For example, if Pn could be written in the hypergeometric form, then there is hope that you can also show that the second line also preserves hypergeometric form.
Probably, I really don't know that, but I haven't seen that.
Nobody did that actually. Right?
I haven't seen that.
No,
I don't know.
That's it. That's it. Thank you.
Okay.
It can be like a linear combination of several polynomials. No?
It is. This in the scalar case, this is actually a linear combination of your. For example, if you have Laguerre polynomials,
Right.
and you construct like Laguerre-type Sobolev polynomials, then what you get here is a linear combination of Laguerre polynomials. So I'm not sure if you have a linear combination of hypergeometric functions, they can be expressed as a new
Not always. No, it's
so
clear that not always.
okay.
More questions?
I have one more.
Okay.
Can you go please to the orthogonality when in two variables, and when you need to divide? Yeah, this one. Yeah, this one. Is that correct that it was first Tratnik who noticed that you should multiply omega xy in this particular ugly way, and when omega 2 is just one y divided by rho x? It was Tratnik first?
I believe Corwinder. Corwinder did this. Corwinder, yes.
Corwinder.
Yeah.
Okay.
Yeah.
Very good. Yeah.
Yes.
The point is that I still don't like that, meaning that I hope that with time we will get something other, but still people use that, right?
Yes.
Yeah.
Yes.
It's easy to prove the orthogonality. If you do this, then the orthogonality appears very easily.
No, it's clear, Ivan. I know, but what appears easily not always beautiful, right?
Don't tell me.
Okay. Thank you.
Yeah.
Okay, understood.
So no more questions. So let's thank Luis again.
Thank you.